Hello, in this video, I will derive using logarithmic differentiation. So what is logarithmic differentiation? It's just another technique to differentiate more complex equations. When would I use logarithmic differentiation? Anything with the radical exponents or an ln in the equations. So for example, y equals the fifth root of x minus 1 over x plus 1. Why should we use logarithmic differentiation? Because it does have, it's technically is exponent, right? You can rewrite this as x minus 1 over x plus 1 raised to the 1/5. So yeah, you can definitely use logarithmic differentiation for this one. Okay, let's move on. Okay, so the next slide is steps for log. Now you can determine when. Now let's talk about the steps for logarithmic differentiation. So first step is take the logarithm or the ln of both sides. The next step 2 says expand using your laws of logarithmics. Step 3 says take the derivative of both sides. You can use implicit differentiation, chain rule, derivative of logarithmic rules. And then the derivative of ln of u is u prime over u. And then step 5 says find y prime or get y prime by itself. Y prime is the same thing as dy dx. So you don't, if you want, you can replace y prime as dy dx. It's the same thing as y prime. And then yeah, just find y prime or dy dx by itself by replacing y with the original function. Reviews of properties of logs. So there's like 5 log rules you can when you expand and when you're multiplying. So let's say you have ln of mn. When you're multiplying logs with this, you really are adding, and when you're dividing logs, you're really subtracting. When you have a log raised to a certain power, when you expand it, you put the power in front of that natural log or log. And then ln of e, if you have an ln and an e, they are inverses, so you're just left with the power, okay? And then ln of 1 is 0. Let's try doing 2 examples. So let's do this example right here. Let's use blue. So first step says we got to take the ln of both sides. Okay, so we took the ln of both sides. And then the next step is we use properties of logs to expand it. So e on the right side, e to the x is an exponent. So when you have an exponent and you want to expand, you put the power in front of the log or the natural log. So this could be expressed as e to the x times it by ln of x. And then on the left is ln y. The next step is take the derivative of both sides in respect to x. So on the left side, what is the derivative of ln of y? It's 1 over y, and then chain rule, y prime is 1. And then in respect to x, it's going to be dy dx. Or you can call it, you can replace dy dx with y prime. It's the same thing. Now, what about on the right side? How do you take the derivative of this in respect to x? You would have to apply product rule, right? So if my f is e to the x, my f prime in respect to x would be e to the x times 1. And then you do have the option of putting dx over dx, but that just becomes 1. So really, it's just e to the x. And then my g is ln of x. G prime is 1 over x, and then dx over dx, which becomes 1. Okay, so yeah, G prime is this. Now apply product rule. So product rule is f prime of G plus G prime of f. So f prime is e to the x times it by regular G, which is ln of x, plus G prime, which is 1 over x, times it by regular f, which is e to the x. And on the left side, you get 1 over y, and then dy dx. Okay, so on the right side, is there anything we can simplify, or is there anything we can take out? Yes, we can. We can take out this e to the x. So let's factor out that e to the x. And then you have ln of x plus 1 over x. And the left side is 1 over y dy dx. And then to solve for dy dx, you have to get rid of this 1 over y by multiplying both sides by y. So you have dy dx equals to y, and then you have times it by e to the x ln of x plus 1 over x. And then what you do is replace y with the original function. So our y was x to the ex. So your final answer, let me put it right here, dy dx, or y prime, is going to be y, which is x raised to the ex. And then you have this times it by this whole thing. That would be times it by e to the x 1 over x plus ln of x. And that's your final answer. Okay, go ahead and pause and copy the work so we can move on to example 2. Okay, let's move on to example 2. So find the derivative by using logarithmic differentiation. So let's start with the first step. You're going to take the ln of both sides. Wait, is there anything we could do to make this more simple? I guess I can, on the right side, I could put everything in power. So if you want, this is already in power, so it's x plus 2 squared. And then on the bottom, square root of x squared plus 1, that's equivalent to saying x squared plus 1 raised to the 1/2, right? So I think that'll be helpful. So we're going to take the ln of that whole thing. And then what we're going to do is expand using your log rules. So let's see here. The top can be expressed as ln of x plus 2 squared minus ln of x squared plus 1 raised to the 1/2, right? And then we can expand this even more. This is a power of 2, so you put the power in front of the ln, so it's 2 ln of x plus 2 minus this has a power of 1/2, so you put it at 1/2 ln x squared plus 1. And then what we'll do next is just take the derivative. So on the left side, the derivative of ln of y in respect to x is 1 over y, because the derivative of ln of y is 1 over y. And then you have to add that dy dx. On this side here, what's the derivative of this whole thing? Well, the derivative of ln x plus 2, this 2 is a constant, so you could just bring that down later on. But what's the derivative of ln parentheses x plus 2? It's 1 over x plus 2 times the derivative of the inside. So the derivative of x plus 2 is 1. Okay. Minus 1/2. And then since 1/2 is a constant, just put it out for a bit. And then what's the derivative of ln of x squared plus 1? It's 1 over x squared plus 1 times it by the derivative of x squared plus 1, which is 2x. So looks like the 2's cancels. So let me put it right here. So on the left, you're left with 1 over y dy dx equals to 2 over x plus 2 minus, see the 2's cancel, so you're left with negative x over x squared plus 1. What could we do? I guess if you want, you can simplify this before we get dy dx. So 2 over x plus 2 minus x over x squared plus 1, we're subtracting, so we need a GCF. So my GCF would be the mixture of x squared plus 1 times x plus 2. So this one is missing in x plus 2. And this is missing in x squared plus 1. So this is going to be 2x squared plus 2. If you FOIL this out, this is x squared plus 2x. And if you FOIL that minus, that would be minus x squared minus 2x. And then if you clean that up, block like terms, so x squared minus 1x squared is x squared. I mean, just 1x squared, right? 2x squared minus 1x squared is x squared. And then you have negative 2x plus 2. And then on the bottom, it's just the x greatest common factor. And then you have 1 over y dy dx. And then solve for y, so you're going to multiply everything by y. So you have dy dx. So when you do that, the left side is dy dx. And then we have, so we're multiplying both sides by y. So this is going to be y times this whole thing, right? And then just replace y with the original function. So when you finally do that, when you collect like terms, you're going to get, I gotta erase this. Your final answer is going to be dy dx equals to x plus 2 x squared minus 2x plus 2 over x squared plus 1 raised to 3/2. And that is your final answer. Okay, go ahead and pause. Go ahead and pause to write down the work, and I'm going to stop here, and then we'll do the other two examples on the next video, and then the quiz. Okay, thank you. Bye-bye.